Alright, welcome. In this video, I'm going to be working through Linear Algebra Quiz 2.2, which was about linear transforms. And this one was one we did as in groups in class or something, and I had said I would record solutions to it, so I'm going to do that now. Alright, so we're going to start off by writing a matrix M, where if x is a two-dimensional vector, m times x rotates x counterclockwise 60 degrees. Alright, so we're just writing basically a transformation matrix. And so what we want to do here is think about, what happens when I do m times I. That'll be the first column. And then whatever happens when I do m times j will be the second column. Well, mx rotates x counterclockwise 60 degrees. So what I'm going to do is I'm going to start with I, and then I'm going to rotate it 60 degrees. Okay, so it's going to go up like that. And that's not a very good diagram. Let me actually rotate that a little better. I like that a little better, and we know that if it's a 60-degree angle here, that's a 30, 60, 90 triangle, and this is going to be a half, and that's going to be root 3 over 2. Okay, so the landing spot for vector I is x equals a half, and y equals root 3 over 2, so that's what we're going to do. We're going to go write that in here, say, all right, x is 1/2, and y is root 3 over 2. And then for j, we're going to start off here. Okay, j is the vector where x is 0 and y is 1. And then we're going to rotate that 160 degrees, so that would be almost all the way over here. And then I'd look at x and y. Over here, same story, 30, 60, 90 triangle. That's going to be a half. This will be root 3 over 2. We're going to label that. Okay, but since we're over here where x is negative, this will be negative root 3 over 2. And so x is negative root 3 over 2, and y is positive 1/2. Okay, and I think that's better than just like memorizing the standard rotation matrix for 2x2 vectors. Specifically because that mindset would help you solve this one much easier. So the projection of a point in space onto the xy plane is a linear transformation from R3 to R2. All right, so if we're going from R3, then we're kind of starting off with three basis vectors, I and j and k. And then the matrix that represents the linear transformation will be, well, whatever happens when I do the transformed I and j and k, those will be the columns of my matrix. Okay, so if I run I through the transform, well, that's a point that just sits right there on the plane. So nothing really happens to it, so it stays I. And j, probably the same story, right? It's already on the xy plane. So if I project it onto the xy plane, it's not going to go anywhere. It's going to be still 0, 1. But then k, which is up here, this one going up, if I project that down onto the xy plane, that will hit the origin. So that's going to go to the point 0, 0. And so I would say that, all right, the matrix that represents this transformation is going to be 1, 0, 0, 1, 0, 0. It's the landing spot of all three basis vectors. All right, now this next one, there's a variety of ways to do. I guess there's probably a variety of ways to do all these, but this one I can really see how you could do this one some other way. I'm going to kind of keep on the same theme and see that, all right, well, the matrix A is just going to be made up of, pardon me, let's see, that's a little off of a shot. T of I and T of j. And so really what I need to figure out is what is T of 1, 0 equal to, and what is T of 0, 1 equal to. And with this 1, 1, and 1, negative 1, I guess, I'm trying to remember what I was envisioning when I wrote this problem. I'm not sure if this was what I was envisioning. Maybe there's an even slicker way to do this problem, and if that is something you're seeing, let me know, and I'll share it with the whole group. But let's see, where am I? There I am. The clearest way I see to go is to take T of 1, 1 plus T of 1 and negative 1. And the thing about a linear transform is that it's the same, it's like adding on the inside. So that's going to be T of 1 plus 1 is 2, and 1 plus negative 1 is 0. But also, okay, there's the thing about constant multiplication. So that's 2 times t of 1 and 0. All right, so what I need to do is go back to what I had asked for in the first place, which was adding the two vectors I was given, and that's 2, 2. Now if 2, 2 is over here equal to twice what I'm looking for is going to be 1, 1. Okay, and that's going to be t of I. So go over here and say, all right, that was 1 and 1. And then t of j, I'm going to probably need to figure that out by subtracting. Yeah, if I take t of 1, 1, and I subtract t of 1 and negative 1, that would be equal to t of 1 minus 1 is 0, and 1 minus negative 1 is positive 2. And that's twice t of 0, 1, which is what I'm looking for, t of j. Okay, so over here, that's going to be equal to, if I subtract them, 0, 2 minus 2, 0, that'd be negative 2 and 2. And then I'd need to divide that in half, and so it's going to be negative 1, positive 1. Okay, and that's going to be matrix A. Okay, for number 4, let f, which maps R2 into R4, be the linear transformation with f of 1, 0 is this, and f of 0, 1 is that. Okay, that means that f of x is equal to 0, 3, 1, 1, and 1, 0, negative 1, 2 times x. Okay, that's the matrix for it. But I actually don't think that's going to be the way to solve this problem. I mean, it's all equivalent. You're going to do all the same calculations just because of the row picture and the column picture being two sides of the same coin. But what I'm going to say is, all right, well, f of 2 and negative 3, I'm going to use the linearity of the linear transform and say, all right, that's going to be 2 times f of 1 and 0 minus 3 times f of 0 and 1. If you look at it and think, okay, well, I'm being taken 2, 0 minus 0, 3, that's going to give me 2 and negative 3. All right. And then I'm going to say, all right, that's 2 times 0, 3, 1, 1. 3 times 1, 0, negative 1, 2. That's going to be 0, 6, 2, 2, plus, I'm going to distribute the negative 3 over everything. And then that's going to be 0 plus negative 3, 6 plus 0, 2 plus 3, and 2 plus negative 6. Alright, g of x is going to equal a times x, where a is the matrix. This is a 3 by 2 here, let u equal this, and v equal that. What are the domain and codomain of g? Alright, so g of x equals a times x, so if we envision, a vector x going here, it's going to need to be a two-dimensional vector in order for the multiplication to be defined. This is a 3 by 2. We'd have to multiply by a 2 by 1 if it was going to be a vector. It needs to be a two-dimensional vector. That means G takes R2 into R3. And because it would give you back a 3 by 1 matrix. So we would say that the domain is R2 and the codomain is R3. Okay, find G of u and G of v. All right, well, G of u would equal a times u, because I said g of x is a times x. So that's going to be 1, negative 1, negative 1, negative 2, 3, and 4, multiplying by u, which is 2 and 3. Right, now you can do the dot product way. I'm going to say, okay, multiplying matrix by vector like this, it looks pretty easy to just do 2 of the first column plus 3 of the second column, and that's, an equivalent way of looking at matrix multiplication. So I'm going to say 2 times negative 1, negative 1, negative 1, plus 3 of negative 2, 3, and 4. That's going to equal this 3 times 3 and 3 times 4. And then that will be, let's see, -4, +7, and +10. All right. And then for g of v, okay, that's going to equal a times v, which is going to be, I guess I'm not even going to say equals, I'm going to say is not going to exist. D and E is that the dimensions are mismatched, right? A is a 3 by 2, and V is a 3 by 1. Okay, those dimensions don't match up, so I'm not going to be able to do that multiplication. That doesn't exist. Okay, a three-dimensional vector, that's an element of the codomain, but not an element of the domain. It's it's undefined. It's not in the domain. All right, G inverse of U. Okay, that's where we say, all right, G inverse of U. That's where we're solving the equation G of X equals U. Okay. So that would be AX equaling, that was U 2 and 3. And if we're going to go solve a matrix equation like this, we need to probably go row reduce. And if we were going to go try to augment with this vector 2, 3 against A, it wouldn't work, right? A is too tall. The dimensions are mismatched. U is a two-dimensional vector, and that's not in the codomain, so I can't look and see, is it an actual output value of G? Okay, so this doesn't exist either. It's outside of the codomain. And then G inverse of V is where we're going to be solving the equation G of X equals V. Okay, so that's AX equaling, what was V? 0, 2, 4. All right, so if we're going to want to solve this equation, we're going to need to row reduce a matrix. All right, so I take matrix A, I augment it with V, and I'm going to row reduce it. And this one's really set up, for us to row reduce well. So we're going to add row 1 to row 2 and row 3, and that's going to give me 1, 0, 0. This will still be -2 and 0. And then if I add -2 to 3, I'll get 1, -2 to 4, I would get 2, and this will still be 2 and 4. All right, so then I can see that the 1, 2 is going to stay there. And we could kill off that bottom row and have a row of all zeros. Okay, and then I'm going to have from there, I'm going to probably add 2 of row 2 back up on row 1. Have 1, 0, 4, 0, 1, 2. Right, and then, just give myself the visual reminder there. Okay, I've got myself a fully reduced matrix, and what this is saying is that x1 equals 4 and x2 equals 2. Notice I didn't say x3 can be whatever it wants. I don't have enough columns to be talking about x3. Moreover, I'm solving for the vector in the domain of G that gives me an output of V. The domain of G is R2. So I'm looking for a two-dimensional vector, and that's why I have one solution, and it's 4, 2. The G inverse of V equals the vector 4 and 2. Not sure if that's, it was not still on there, but there you go. All right. Okay, for form Q, now we're gonna go, and it looks like this is kind of what was on the back side. Is this the exact same problem? No, it's not exactly the same, so I'll do it. G of X equals A times X, where A is the matrix, A equals, it's a 3 by 2 here. What are the domain and codomain of G? Okay, well, make a little illustration. Right, so we're thinking about, what's happening here with this function, and we're taking a vector and we're multiplying it by A on the left, and we're getting an output vector, G of X. Right, so A times X. A is a 3 by 2 matrix. So that means that if X is a vector, it needs to be 2 by 1. It needs to be some number of, entries in a 1-column matrix. And so it's going to be, X is going to be 2 by 1. And as a result, G will be 3 by 1. Okay, so x is the input, right? Is the input variable here. So it's a 2 by 1 vector. That means the domain is R2. And then the output is 3 by 1. That means the codomain is R3. All right, now we're going to have g of u and g of v. G of u is going to equal a times u, and a was 1, negative 1, I think negative 2, 3, and 4, yeah. And then u was 5 and 2, so that's going to equal 5 of the first column plus 2 of the second column. So 5 plus 4 is 9. Negative 5 plus 6 is 1, and negative 5 plus 8 is 3. Alright, so it was 9, 1, 3. G of v is going to equal a times v. I don't really like how I wrote those parentheses there. I mean, I guess it's fine, but it's a times u and a times v doesn't exist because of the dimension mismatch, right? A is a 3 by 2 and v is a 3 by 1, and you see those two numbers there are not the same, so the thing does not exist. All right, g inverse of u and g inverse of v, that's what we're back solving. We're saying, all right, g inverse of u, that's where g of x equals u. Okay, this doesn't exist because you use a two-dimensional vector, and that's the domain, not the codomain. Inverse of v, that's going to be solving the equation g of x equals v. Okay, so that's 1, negative 1, negative 1, negative 2, 3, 4, multiplied by x equals, what was v, 5 and 2? No, that was u. Negative 4, 7, 10. I know that's familiar. All right, so what we're going to do is we're going to augment a with v and row reduce, and that will help us solve the system. So 1, negative 1, negative 1, negative 2, 3, 4, augmented with negative 4, 7, and 10. And no, I'm kind of assuming you just fast forwarded to form Q and you didn't just watch me do this the exact same row reduction with the other matrix. But I'm going to add row 1 to row 2 and row 3, so I'll have 1, 0, 0. Row 1 will be unchanged, and then I'll be adding negative 2 to 3 and negative 2 to 4. Then I'll be adding negative 4 to 7 and negative 4 to 10. Okay, so I'm seeing 1, 3, 2, 6, and I know I'm going to be able to completely eliminate that 2, 6. And 1, 3, that's as reduced as we're going to want to make it. And then I guess from there I can also add 2 of row 2 back up onto row 1 to eliminate that negative 2. And then I'll be adding 6 onto the negative 4. And so I've got it fully reduced. Okay, I can add that bar in to aid my eye to see that x1 needs to equal 2 and x2 needs to equal 3. And those are the only two variables, right? I'm solving back for an element of the domain that got me to g of x equals v. And so the domain is R2. It's going to be a two-dimensional vector that I'm looking for. All right, so I'm going to say x equals 2 and 3, or maybe you could say g inverse of v is equal to 2 and 3. All right, on the back, write a rotation matrix for counterclockwise 30 degrees. All right, so we're going to figure out what happens to I, and we're going to figure out what happens to j. All right, if we go clockwise 30 degrees, it's going to make a 30, 60, 90 triangle. Dimensions would be 1/2 and root 3 over 2. Let's see what we're thinking here. Oh, so, what happens is m times I is going to be the vector x is root 3 over 2 and y is 1/2. And then m times j is going to be, okay, well, I rotate that. That's a little long. Rotate that 30 degrees. And then looking over here, all right, x is going to be negative 1/2. Y is going to be positive root 3 over 2. And the length of the vector is still 1, because j is a unit vector. And then say, all right, m times j, x was negative 1/2, and y was positive root 3 over 2, right? M is just going to be, whatever happens to m times I in the first column and m times j in the second column. So that's going to be root 3 over 2 and 1/2, first column, second column, negative 1/2, and positive root 3 over 2. All right, number 5. The projection of a point in space onto the xy plane is a linear transformation from R3 to R2. So we've got three basis vectors. Right? We've got I along the x-axis, we've got j along the y-axis, we've got k along the z-axis. Oops, that's not right. All right. Now, the matrix that represents the linear transformation is going to be whatever happens when I do the transform to I is going to be the first column. The second column will be what happens when I do the transform to J, and the third column is what happens when I do the transform to K. All right. So I think what happens to I when I project it down onto R2, onto this plane that we've got here illustrated, and nothing happens because it's not above or below the plane, it's already in the plane. So it's going to stay as I, and its coordinates are 1 and 0. Or really, I guess it would lose its z coordinate, but it didn't really have one in the first place. J is going to be in the same story. It's already in the xy plane. It's vector 0, 1. If we take the z coordinate away, which is what we're doing if we're just kind of projecting from R3 onto R2, so we're just completely ignoring z and saying, what point is it above or below? And then t of k, well, what happens to the 0, 0, 1, what point is it right above? It's right above the origin, so we put 0, 0 there. All right. Number 6 is we're going to have a transform here. Yeah, I worked this one on the other form, and I'm not totally sure what I was getting at here, if I was expecting you to do this, or if I thought maybe I was going to do some practice problems, I just forgot to. What I'm going to do is say, all right, A is going to equal what happens to t of 1, 0 is the first column, and the second column will be what happens when I do t to 0, 1. And I can figure out what happens to t at 1, 0 by taking what happens to t of 1, 1 and adding it to t of 1, negative 1. Because t is a linear transformation, this is going to be equal to t of whatever I would get if I added the inputs. So that's going to be x equals 2 and y equals 0. Right? Now, it also has the property that I can kind of factor out a 2 from it and say this is twice t of 1 and 0. It's the thing about the properties of linear transforms. And so if I actually added those two vectors together that was given, 0, 6 and 6, 0, I'd get 6, 6. Right, so if 6, 6 is 2 times what I'm looking for is going to be 3, 3. The same thing, I need to move that down a little bit. We do the same thing with t of 0, 1. And we're going to find that by subtraction. So t of 1, 1 minus t of 1 and negative 1, that's going to equal t of 0 and 2. And I can do the same thing, factor out the 2. It's going to be twice what I'm looking for, but if I were to subtract those two, 0, 6 minus 6, 0, I'd have x equals negative 6 and y equals positive 6. And so if that's 2 times what I'm looking for, what I'm really looking for is negative 3 and positive 3, and that's going to be A. Okay, but I wouldn't worry too much about that type of problem. This last one here, f is going to be the linear transformation with f of 1, 0 equals this, and f of 0, 1 equals that, f of 2, negative 3. Okay, I'm just going to point out that f of x, the matrix that represents the transform f, is going to be 1, 4, 2, negative 1, and 0, 1, negative 1, 5, because 1, 0, and 0, 1, those are the standard basis vectors. It's going to be that multiplied by x, but that's, again, just like on the other form, not how I'm going to solve this. I'm going to say that f of 2 and negative 3 is going to equal twice f of 1, 0 plus, yeah, I guess negative 3 times f of 0, 1. So I'd say that's 2 times 1, 4, 2, negative 1, minus 3 times 0, 1, negative 1, and 5. That'll be 2, 8, 4, negative 2, plus 0, negative 3, positive 3, negative 15. And then that's going to equal 2, 5, 7, and negative 17. Oh, and that's not even close to on the shot. Okay, well, hold on, what do we got going on here? Okay. Alright, there you go, that's what I've got. That's going to be all for this video. Thanks for watching.